Okay, today we are going to talk about three-phase circuit analysis. So, go ahead and write that down. Specifically, we are going to be talking about balanced three-phase circuit analysis. All right, so I'm going to draw a circuit for you guys. So this will be VAN, VBN, and VCN, which makes this node our neutral. This is my A terminal of my transmission line network, the B terminal, the C terminal, and this guy here is also the neutral terminal because they're connected together by a short. Then I may have some impedance for my transmission line. So I'm going to call this guy ZWA. And this guy will be ZWB. And this guy will be ZWC. And this guy right here will be ZN. Finally, I need to connect my load. So let's call this guy ZYA. This guy ZYB. This guy ZYC. And this node will also be capital N. So this is an example of a Y-Y system because we have a Y-connected source and a Y-connected load, and the two sides of the system are connected together with a transmission line network, okay? This circuit is considered balanced under the following criteria. All right. So the first criterion is that the magnitude of the phase voltages at the source are equal. So that means that the magnitude of VAN is equal to the magnitude of VBN is equal to the magnitude of VCN. And so we could just as easily refer to all three of these voltage magnitude as VP, where P stands for phase. So they all have the exact same phase voltage. We need the phase separation between the phase voltages to be 120 degrees. So that means that angle BN is equal to angle AN minus 120 degrees, and angle CN is equal to angle AN minus 240 degrees. And this is for a positive phase sequence. Alternatively, So I'm going to do this as a different thing. We could have theta BN is equal to theta AN plus 120 degrees, and theta CN is equal to theta AN plus 240 degrees. So this would be for a negative phase sequence. We have to have one or the other. Obviously can't have both simultaneously. So as long as one of those two conditions is met, things are balanced. Our transmission line impedances need to be equal. So that means that ZWA has to be identical to ZWB, has to be identical to ZWC. So we might just refer to all of these together as Z wire. And I want to make a point to note here that the impedance of the neutral conductor does not have to be the same as the transmission line hot wire impedances. It doesn't hurt anything if it is, but as we'll find out, it also doesn't hurt anything if it isn't, okay? If you were to look into the NEC code, you would see that the size requirements for the neutral wire are very different than the size requirements for the phase wires. And we'll talk about why that is shortly. Another condition for the circuit to be balanced is that the load impedances for each phase also have to be equal. So ZYA would have to be equal to ZYB, would have to be equal to ZYC, and we will likely just call that ZY, okay? So we can observe what the effects of a balanced three-phase system are by determining the line currents in our system. So just for the sake of argument, I'm going to go ahead and define these line currents here. I think I did it in blue the other day, so I should probably do it in blue today as well, just to be on the safe side. So here's our line current for the A phase. Here's our line current for the B phase. Here's our line current for the C phase. And while I'm at it, our neutral conductor will have an associated line current as well, if it exists. Okay. So another thing that I'm going to do to make our analysis a little bit easier here is I am going to select a neutral node as a reference. So that's just going to be considered our 0 voltage point for this system. I am going to do that arbitrarily here. So the source side neutral, we are going to consider to have a voltage of V is equal to 0 volts RMS, okay? And that's just to make our math a little bit easier. All right. So if we apply Kirchhoff's current law to our left-hand lowercase neutral node, we're going to see that IAA plus IBB plus ICC plus INN all together must equal 0, right? So I'm going to go ahead and write that down. I can use Ohm's law to re-express this quantity, okay? And so what I mean by that, my line current, IAA, using Ohm's law, so that current is originating at this point, and it's terminating at this point. So I would have for IAA, it would look like V lowercase a lowercase n minus V capital N lowercase n. So those are my two voltages at the different points, divided by the series impedance seen by that current, which in this case would be ZWA in series with ZYA. Does that make sense? Okay, so I'm just using Ohm's law. I have VAN minus V capital N lowercase n divided by ZWA plus ZYA plus VBN minus VNN over ZWB plus ZYB plus VCN minus VNN over ZWC plus ZYC. Now we need to look at something real quick for our neutral conductor, right? So our current through our neutral conductor is originating at lowercase n and terminating at capital N, right? So it looks like it should be 0 minus VNN divided by ZN. So I'm going to put minus VNN divided by ZN equal to 0. All right. If our network is balanced using the constraints that we identified earlier, then this will reduce. We will have V capital N lowercase n divided by Zn will be equal to VAN minus VNN divided by Z wire plus ZY plus VBN minus VNN all over Z wire plus ZY plus VCN minus VNN all over Z wire plus ZY. And so I can see that I have a common factor of negative VNN over Z wire plus ZY. And I'm going to move that over to the left-hand side. Okay. And so what that's going to do, I'm going to get the following expression. VNN will be multiplied by a factor of 1 over Zn plus 3 over Z wire plus ZY is equal to VAN plus VBN plus VCN all divided by Z wire plus ZY. So everybody okay with the algebra that I have just done here? Because this is actually a critical step, okay? Everybody okay with things? If you got a question, by all means, ask it. All right, nobody's saying much of anything, so let's move forward. So let me scroll down to the next page here. If our source is balanced, meaning that it has equal magnitude of the phase voltages and exactly 120 degrees of phase separation between each phase, we can say that VAN plus VBN plus VCN is equal to VAN plus VAN times one angle negative 120 degrees. Here I'm assuming a positive phase sequence plus VAN times one angle negative 240 degrees, which would then be VAN multiplied by one angle 0 plus one angle negative 120 plus one angle negative 240 degrees. Is everybody clear what I've just done? I'm listing all of my three different phase voltages with my voltage VAN as effectively a reference. Now, one of you guys grab a calculator, please, and figure out what one angle 0 plus one angle negative 120 plus one angle negative 240 is. Zero. That means the sum of these three voltages together must equal to 0. So if we look back at our previous equation, Z wire plus ZY is assumed to be some non-zero quantity, right? We're assuming that there is some impedance. Similarly, Zn is assumed to be non-zero. So I have 0 divided by some finite number is equal to a finite number times my neutral to neutral voltage. So what does that neutral to neutral voltage have to be? It also has to be 0, okay? So from this, we can see that V capital N lowercase n is equal to 0 volts for a balanced three-phase system. Okay, this is very, very important revelation. So for a balanced system, the voltage drop over that neutral conductor is 0 volts, regardless of what the impedance of the neutral conductor is. So if it's a short circuit, the voltage drop across it is 0 volts. If it's an open circuit, meaning it doesn't exist, it is not physically connected, there is no wire connecting the neutral side of the source to the neutral side of the load, the voltage drop is still 0, okay? That's very, very important, all right? So for a balanced three-phase system, we don't even have to have a neutral conductor at all, because we know if there's no voltage drop over it, there can be no current flowing through it either, okay? So let's go ahead and explicitly state that as well. INN, our neutral conductor current, is going to be negative V capital N lowercase n divided by the impedance of our neutral conductor, and it has to be 0 as well. The reason why I have the negative sign out in front is because I have the opposite order of my subscripts, which means I have to multiply by a factor of -1, right? My neutral conductor current is defined as flowing from the source side neutral to the load side neutral, but my voltage is defined from the load side neutral to the source side neutral. So that's where that negative sign came from, but it doesn't matter because it's all 0. Okay, so if we wanted to look at our line currents then, our line current IAA will be VAN minus VNN all over ZWA plus ZYA, which for our balance system reduces to VAN divided by Z wire plus ZY. Our line current IBB is then going to be VBN minus VNN over ZWB plus ZYB, which looks like VBN over Z wire plus ZY, and because we have a balanced source, this is just VAN divided by Z wire plus ZY multiplied by a factor of 1 angle negative 120 degrees. And finally, our line current ICC is going to be VCN minus VNN over ZWC plus ZYC. Looks like VCN over Z wire plus ZY, which is nothing more than VAN divided by Z wire plus ZY times 1 angle negative 240 degrees. Okay, so for a balanced system, we have observed that our line currents, because our voltages, our source voltages are 120 degrees out of phase, and all of our impedances are perfectly matched, our line currents have the exact same magnitude, and they are also 120 degrees out of phase with each other, okay? As a consequence of that, let's go back up to our original circuit, all right? So if our line currents are perfectly balanced, meaning that they all have the same magnitude and they are 120 degrees out of phase with each other, what can I say about the phase currents flowing through the load? They all have the same magnitude and they are all 120 degrees out of phase with each other. Since those line currents are perfectly balanced, what can I say about, or excuse me, since those phase currents are perfectly balanced, what can I say about the phase voltages at the load? They are perfectly balanced. What can I say about the line voltages at the load? They're perfectly balanced. If we have a perfectly balanced system. All of the magnitudes of our different quantities are the same, and they are all separated by exactly 120 degrees, okay? So we can take this big, ugly three-phase system that took a little bit of work to analyze and actually break it down into three identical single-phase equivalent circuits that we can analyze. And if we can analyze one of those, we can get all of the quantities for the other phases as well, okay? So our single-phase equivalent circuit, let me scroll down here. Equivalent. So for the balanced YY circuit, we know that the neutral voltage is 0 and the neutral current is 0, which means there is no voltage drop across the neutral conductor. We can treat the neutral conductor as a short circuit regardless of its impedance, even if it is actually equal to infinity, which we talked about a moment ago. So we can divide our balanced three-phase YY network into three independent single-phase equivalent circuits. So for our A phase, it's going to look something like this. Where you can easily determine the value of our line current for our B phase. It'll look something like this. And for our C phase, it'll look something like this. See. All right, let me go ahead and define those line currents again. IBB. And ICC, okay? So we can break down a YY system into three independent single-phase equivalent networks, where, just to be very clear here, we only actually need to be able to analyze one of them to get all of the other quantities. Because let's say if we analyze the A phase, we know that every quantity in the B phase is just going to be lagging it by 120. Everything in the C phase is going to be lagging it by 240. If we were to analyze the B phase, we know that the A phase is leading by 120 and the C phase is lagging by 120, etc. So if we can analyze one of these circuits, we should be good to go. So here is the million-dollar question. Do you guys feel that you can analyze a circuit like this, containing a voltage source and two impedances in series? I certainly hope so at this point in your EE career, okay? So analyzing a YY system is utterly trivial, all right? It's the easiest possible circuit that we could ever analyze. The question then becomes, how can we make non-YY circuits look like a YY circuit, right? So how do we make a delta connected load look like a Y connected load so that we can use our single phase equivalent circuit? Or how do we make a delta connected load look like a Y connected load so we can do it? Yes, sir. Mm-hmm. Yes, so this only works for a balanced three-phase system, okay? So that's why I'm using Z-wire and ZY, not ZWA and ZYA. If it's not balanced, we can't do this. We have to actually use all of this horrifying math where all of the assumptions that we have made about it being a balanced system have to be ignored, okay? So for an unbalanced system, the analysis is quite rigorous. For a balanced system, the analysis is extraordinarily trivial, okay? All right, so we're gonna spend the next half an hour or so developing transformation techniques to make delta connected things look like Y connected things and vice versa. Once we get that down, we can make any system look like a YY system and then we can analyze it, okay? So let's start with transformation between balanced sources. All right. So let's start with a Y connected voltage source that is balanced, okay? So here's our A phase. Here's our B phase. So it seems this is VAN. Let's consider this guy to be VBN. And then this guy to be V, that's not where that should go at all, sorry. This is the C terminal. This is the neutral terminal. And so this is VCN, okay? Now we mentioned the other day that we can measure line voltages off of a three-phase Y-connected source, right? So for example, we would have a line voltage VAB, like so, measured between the transmission line terminals A and B. We could have a line voltage VBC, and additionally, we will have a line voltage VCA. We can develop mathematical relationships for these quantities, right? So for instance, if I say that VAN has some magnitude VP with an angle of 0 degrees, VBN must have that same magnitude VP with an angle of negative 120 degrees, assuming a positive phase sequence, as we will do in this class. And VCN will be VP angle negative 240 degrees. All right. Our line voltages, VAB. Let's look at what VAB really represents here, okay? If we were to do Kirchhoff's voltage law around this loop, we would see that VAB is equal to VAN minus VBN. Is everybody okay with that? So we have positive polarity connected to positive polarity. So that's why this guy is equal to this guy. And then we see the negative, so that's why it's minus VBN. So we can say very easily that VAB is VAN minus VBN, which is simply VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees, because I know that VBN is nothing more than VAN lagging by 120 degrees. 1 angle 0 minus 1 angle negative 120 is simply the square root of 3 with an angle of positive 30 degrees. Okay. So I can transform my phase voltage into my line voltage by simply multiplying by square root of 3 and multiplying the magnitude by the square root of 3 and adding 30 degrees to its phase angle. Okay, so I have a simple transformation. From this, it should be fairly obvious. VBC is simply VBN times the square root of 3, angle 30 degrees, and VCA is VCN, square root of 3, angle 30 degrees. Okay. So I can use these relationships to convert a balanced Y source and make it look like a balanced delta source, right? Because the delta source is defined by its line voltages. It doesn't have any, I will say line to line voltages. So transmission line terminal to transmission line terminal, not transmission line terminal to neutral terminal, okay? So what I am attempting to say here is that I can go from this here's A, B, C with VAN, VBN, and VCN to this guy, where here's A, here's B. There we go. VBC. VCA by multiplying by root 3 angle 30 degrees, okay? So I can go from the left to the right by multiplying my quantities by root 3 angle 30 degrees. So if I want to do the inverse of this transformation, where I convert from a delta connected system to make it look like a Y connected system, what do you think I have to do? Divide by that quantity, right? So to go the other way around, I simply multiply by a factor of 1 over the square root of 3, and I subtract 30 degrees. So this is the means by which I can convert from Y to delta for a source and from delta to Y for a source. So we have developed a transformation. Everybody okay with this? We're going to see lots and lots of multiplication by root 3 angle 30 and division by root 3 angle 30 in our work here, okay? I've just defined these factors both as a simple multiplication means, all right? That's helpful to me. So are there any questions regarding transformation between balanced sources? All right. So now let's look at transformation between balanced loads. All right. So let's say that I have, all right, this should not be circles because it's not sources. A Y-connected load. Strictly speaking, UIC, our loads do not need to be balanced in order for us to do a transformation. The math for a balanced load transformation is way easier than an unbalanced, but we can go with, we can transform unbalanced systems as well, okay? And so I'm going to talk about how we go about doing that. Here's A, B. So this guy would be Z delta A. Z delta B. Finally, Z delta C, okay? So what we are going to do is we are going to define the Y delta and delta Y transformation. How many of you guys remember way back in homework 1, where I was like, hey, you need to look this up because we're going to use it. It's finally coming to fruition, okay? So the impedances seen between the terminals A and B of the Y load, ZAB, is simply ZYA plus ZYB. And the impedance seen between the A and B terminals of the delta load is Z delta A times Z delta B plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. So effectively, I'm saying that Z delta A is in parallel with the series combination of Z delta B plus Z delta C. And then I multiply those two things together, all right? If I equate these two expressions, I will get 3 equations, okay? I will get ZYA plus ZYB is equal to Z delta A times Z delta B plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. For my next set of terminals, I'll get ZYB plus ZYC is equal to Z delta B times Z delta A plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. And finally, I can say that ZYC plus ZYA is equal to Z delta C times Z delta A plus Z delta B all over Z delta A plus Z delta B plus Z delta C, all right? I can do a Y delta transformation by solving for Z delta A, delta B, and delta C in terms of ZYA, ZYB, and ZYC, which gives me the following relationships. Z delta A is equal to ZYA, ZYB plus ZYB, ZYC, plus ZYC, ZYA, all divided by ZYA. I could say that Z delta B is going to be that exact same numerator, ZYA, ZYB, plus ZYB, ZYC, plus ZYC, ZYA, all divided by ZYB. And then finally, Z delta C is ZYA, ZYB, plus ZYB, ZYC, plus ZYC, ZYA, all over ZYC. Okay, a lot of writing stuff down here. What happens when this is balanced? When we have a balanced system, that means ZYA and ZYB and ZYC are all the exact same quantity, right? So that means we have ZY squared plus ZY squared plus ZY squared, which is 3ZY squared, divided by ZY. This just goes to 3ZY. Same thing for the other two. So for a balanced system, when we're going from left to right, we just multiply by a factor of 3. So I can say that Z delta is 3 ZY. Okay. If I want to go from delta to Y, which means I would be solving for ZYA, ZYB, and ZYC in terms of Z delta A, Z delta B, and Z delta C, I get ZYA is equal to Z delta A, Z delta C divided by Z delta A plus Z delta B plus Z delta C. That's 2, 4. ZYB is Z delta B, Z delta A over Z delta A plus Z delta B plus Z delta C. And finally, ZYC is equal to Z delta C, Z delta B divided by Z delta A plus Z delta B plus Z delta C. When this guy is balanced, what happens? Well, we have, so under a balance condition, Z delta A is equal to Z delta C. So we have Z delta squared over 3 Z delta just looks like 1/3 Z delta. So ZY is equal to 1/3 Z delta. So that is our transformation the other way around. Some groaning going through this, so I just want to tell you guys, be very thankful that I no longer make you guys derive this because that used to be a homework problem. So, yeah. Pretty much no one ever got it right, which is why I dropped it. There's just so much algebra that it gets confusing. Yes?
I'm seeing like a pattern here. So you have like 4 terminals before
I don't know for sure. So if you have 4 quantities, yeah, so I mean, so if you had 4 quantities and you wanted to, so are you trying to change it from a square to an X, or what are you trying to do? And they were all, I don't know. I've never thought about it. I don't want to say yes or no. I literally do not know. Yeah, my biggest question would be how to make it like, so the whole purpose of why the delta Y transformation was created is because sometimes you will have a resistor network that you cannot simplify any other way. But if you had a square of resistors, you can always break that down. It's either going to be two things in series and two things in parallel. It's going to be one or the other, right? Right. Yeah. So here you have something that looks like, when we look through terminals A and B, we see two resistors in series. And when we look through terminals A and B here, we see a resistor in parallel with a series resistance. If we had a square system between A and B, we would see two in series, and between A and B on this side, we would see something in parallel with three things in series. Is that going to work directly as it's multiply by 4 and divide by 4? I do not know. So I'm hesitant to say anything without actually going through all the math and figuring it out. So I don't know. Yes, sir. Yes. So in this class, we're only going to be dealing with balanced systems. So for, well, 99.9% of the time, we're going to be dealing with balanced systems. So the reason why the exclusion is the take-home test. You will be given a problem where you have a balanced three-phase source supplying power to an unbalanced load. So it's purely resistive, and so the math is going to be rather trivial to do, but it is technically going to be unbalanced. And so, but in that particular question, it's a Y-connected load to a Y-connected, excuse me, a Y-connected source to a Y-connected load, so there's no need to do a transformation to begin with. You just have to brute force do the analysis. So it depends. So where I work for in Bossier, we make battery energy storage containers. But some portions of those containers, those container units, run off of the grid, okay? And so the portions that might run off of the grid would be the HVAC systems and stuff like that, okay? So in an HVAC system, you have a compressor, which is typically three-phase, and then you have a fan blower motor and a fan intake motor, which are typically single-phase. And so you have an unbalanced system inherently because you have a balanced three-phase system connected to two single-phase systems, which are going to put the system into imbalance. So what we typically do is if we connect the fan blower motor to phase A and the fan intake motor to phase B on one building, we'll do it B to C on the next building and then C to A on the next building, so that every 3 buildings we have balances everything out. And then we just repeat that over and over and over again so that the total imbalance is going to be very small because we've designed it that way. If we hooked all of the intake motors to phase A and all of the blower motors to phase B, we'd wind up with a very large imbalance that would mess with things. So in practice, with reasonably good design, you're going to see that everything pretty close to balances each other out.
And also we're going to run into three-phase.
In industry, absolutely. If you go into power, you're going to be dealing with three-phase power systems. Like the overwhelming majority of the time. Even if you go into solar, which creates DC power, if you want that DC power to do anything to like power a house, you have to run it through an inverter. The inverter is just a series of switches that makes that DC signal look like a three-phase voltage source. So it's all, you know, well, I take that back. In your home, it might make it look like a single phase, but if you wanted to connect it to the grid, so like if you wanted to sell energy back to a distribution company like Entergy or AEP, SWEPCO, then you'll have to use the three-phase inverter where it balances everything and sends it back so that you don't create too much of an imbalance on their system. So three-phase power is literally everywhere. Doesn't matter if you're generating electricity with, yep, literally right there, all around us. It's all electromagnetic waves, so it's literally permeating our bodies at this very moment. So yeah. All right, so we have developed our transformations and all that kind of good stuff. So let's, before we start analyzing circuits, does anybody have any questions? Let's start there. We've gone through an awful lot of stuff. We've done no actual math really to this point. It's all been kind of abstract. So I just want to make sure we're all on the same page before we start getting our toes wet, as it were. All right, nobody's saying much of anything. So let's jump to an example problem. All right, how many of you have noticed that I've posted the homework assignments and all that kind of stuff? Anybody? Great. All right, so for all the three-phase homework assignments, everything I give you is a word problem. There are no pictures anywhere. And so that's how I'm going to set up the example problems. And then if it helps things, I will talk to you about how to draw the circuit diagrams and all that kind of good stuff, okay? So in this problem, we have a positive phase sequence balanced three-phase Y-connected source supplies power to a balanced Y-connected load. So we're told explicitly that we have a YY system here, okay? The magnitude of the line voltages is 208 volts RMS. If the load impedance per phase is 36 plus J 12 ohms, determine the line currents if the angle for the A phase of the source voltage, angle VAN, is 0 degrees. So this is our problem statement. It is fairly characteristic of what you will be asked to do on your homework and on the exams and all that kind of good stuff. So until you get super comfortable with things, I would argue that drawing a picture is probably going to be fairly helpful, okay? So I'm going to start by drawing a schematic diagram of our system. All right, so first thing that I want to point out, in anywhere in our problem statement, is there a mention of what the impedance is for the transmission lines? Transmission lines are literally the only way that we could connect a Y source to a Y load, or a three-phase source to any three-phase load. Right? So if the transmission line impedances are not given, we are going to assume that they are zero. So we effectively have a lossless system. So I can just connect these guys with a wire. Our ultimate goal in this problem is to determine our transmission line currents. Sorry, this should be CC. Right, not at all. We could if you wanted to. It's not going to hurt anything whatsoever to draw it or to not include it. Okay, it's going to be included in our single phase equivalent circuit because we know that it's going to act like a short circuit regardless. So it's going to be there when we get to our single phase. But here in our three-phase circuit, it literally doesn't matter one way or the other whether or not it's included. So I typically don't because it doesn't do anything. Do you have a question?
Yeah. So whenever you're like here's a noting from your that line current, when you're actually given the answer, does it matter if you say take capital in one point the other direction, or does it matter?
So I typically speaking define my line currents as flowing from the source to the load. So if I ask for line currents, I'm specifically asking for these exact quantities with this double subscript notation. So little a, capital A. All right, so let's talk about what we know, okay? We are told that the magnitude of our line voltages is 208 volts RMS. So I'm gonna write VL is 208 volts RMS. We know that our load impedance per phase, so that means each phase, so ZY, is equal to 36 plus J 12 ohms. And we know that the angle of VAN is equal to 0 degrees. So I'm going to ask you guys a question here. Based on the information that I have provided, do we know what VAN is? If you say yes, tell me what it is. Tell me what it is as an RMS phasor voltage. You're incorrect. Okay. The magnitude of the line voltages is 208 volts. Right. So where are our line voltages measured? Between the transmission line terminals. So that is not the same as the phase voltages because we have a Y connected source. Okay. There's going to be little things like that that are going to trip you up throughout the next couple of days. So that's what you really got to pay attention to the jargon here, or you'll make an easy mistake that will make everything come out incorrectly, okay? So VL this is what we are getting, right? The magnitude of the voltage between the A terminal and the B terminal of our source, okay? So we can't exactly apply our single phase equivalent circuit yet because we don't know what the actual voltage or the actual phase voltage is. So how do you think we'll get it?
ABL. Is that allowed?
You're not wrong. It's absolutely allowed, but I'm lazy. Okay.
That's part of that. There's an easier method.
Yeah.
Okay.
Yeah, I defined a transformation, right? So let's scroll up here. Let's look. I have a method by which, so if we have a phase voltage to get our line voltage, we multiply by √3 and add 30 degrees to the phase angle. So to go the other way around, we should simply divide by the square root of 3 and subtract 30 degrees from our phase angle.
That's the method I was thinking. I just forgot about. Like,
Yeah,
the word
so
voltage.
so we defined it by using Kirchhoff's voltage law, but now that it's defined, we really don't ever have to do that KVL equation again, right? So if we want to go from the line voltages to the phase voltage, and specifically we're looking at the magnitudes here because that's all we were given, we just need to divide that voltage value by the square root of 3, okay? So I can say that VP, my phase voltage magnitude, that does not look like a P at all. It looks like V with a terribly drawn beta, is simply VL over square root of 3, which for our case is going to be 120.089 volts RMS. Typically, we would just call that 120. The reason why I chose to use 208 is because if you were to open one of the breaker panels here in Methkin Hall, or if you were to, I think my office still has a 3-phase system. My old office definitely did, but you might see something along the effects where on the panel, it will say 208/120Y. The 208 is the delta connected or the line to line voltage. The 120 is the Y connected or line to neutral voltages, so that you have access to either of those things depending on how you connect stuff to the panel. Yes?
So if you throw your multimeter on it and you touch 2 different hot lines, it's going to measure 208 volts.
Right. But if you go from a hot line to the neutral, it'll measure 120. Yeah.
Because if you think about it, the magnitude of both are 120, but since they're 3-phase, you
Right.
get a higher
Mhm.
power output.
Yes.
So
So that isn't a 3-phase. So your house, so okay. So for certain stove tops and stuff like that, they require 240 volts. Okay, so your house isn't fed with a single phase 120 volt system. It's fed with a single phase Y connect. So the Y voltage is 240. So the delta connection, I think that would be 400. Let me do the math real quick. I just got to multiply 240 by square root of 3. No, not 240 squared. 240 square root of 3. 415.7. So that's the voltage for a delta connection at your house. But you would typically see it as 240Y. And so you split that single phase into 2 different 120 volt systems by putting a tap at the center and setting that as your ground. So that technically you have access to, from that ground point, positive 120 and negative 120 volts RMS. So that would be considered a multi-phase system, but it isn't necessarily a 3-phase system because it's really just one phase being split into 2 identical phases. So there's no difference in the phase angles. Well, the difference in the phase angle is, if it's 0 on one, it's 180 degrees on the other. So it's not 120 degrees out of phase. If that makes sense. Or if I potentially just confuse the hell out of you. But that's how your home distribution works. So you get a 240 volt and you split it in half by literally just putting a center tap on the transformer, and then you get access to from ground up 120 and then the other way is negative 120. And if you connect things from both of the hot wires, it looks like 240, which is how your dryers and all that kind of stuff get powered. So like a home installation, typically speaking, won't have a need for a 3-phase. So like the transformers outside of here, like on the power distribution poles and all that kind of stuff like that, like they have a big transformer that's sending out 3-phase. Nethkin Hall, because we have a power lab where we run three-phase machines, we actually get a three-phase connection to the building. But across the street to the IASB and to Tech Point and stuff like that, they're probably just running off of a single phase from that transformer because they have no need to have access to all three phases. So you might say, like, if you had a substation or whatever, the A phase might go to one neighborhood, the B phase might go to another neighborhood, and the C phase will go to a third neighborhood, so that hopefully, roughly speaking, all of those balances cancel each other out so that the system looks reasonably balanced. So like, you know, one street might be connected to the A phase, the other street might be connected to the B, and a third street will be connected to the C. Does that make sense? Okay. All right, so circling back around to this problem, which we have less than 3 minutes to finish now. We can now construct our single phase equivalent circuit. So here is A, here is VAN, here is N, here is Z wire, which we know to be 0. Here is ZY. This is capital A, this is capital N. We want our line current, IAA. So how would we go about getting that using our single phase equivalent circuit?
It'll be our VAN.
That is literally it. So that would be 120.089 angle 0 degrees volts RMS, because we were told what the angle for the A phase was, divided by our line impedance, our Y impedance of 36 plus J12 would give us a line current of 3.165 with an angle of negative 18.435 degrees amps RMS. So now, how would we figure out our line current for our B phase? Pardon? Yeah, just change the angle. Literally just subtract 120 degrees from this. You do not need to do any extra analysis or anything of that sort, okay? So it's just going to be 3.165 with an angle of negative 138.435 degrees amps RMS. And finally, ICC would be 3.165 with an angle of negative 258.435 degrees amps RMS. Once we get it to our YY system, we only have to solve it once, and then we can get every other quantity that we need just by shifting by 120 degrees. All right, I ran out of time, so unless you have any questions, we're going to wrap up for today, and then I have, I think, 7 more pages of example problems to work for Friday. So to get us familiar with the different types of systems and doing all the transformations and all that kind of good stuff.
We're supposed to multiply by or divide by square root of 3 angle negative 30 degrees.
Okay, so the reason why I didn't care about the angle is because I was already told exactly what my angle for the A phase was, and I was only given the magnitude of the line voltage. So I had no reference voltage to, or excuse me, reference phase angle to subtract 30 degrees from. So a different variation of this problem might be the line voltage VCA is 208 angle 60 degrees. From that, you could definitively determine what VCN is by dividing by square root of 3 and subtracting 30 degrees. And then you would subtract, or excuse me, you would add 120 degrees to get to the A phase. But because we were dealing with a magnitude of our line voltage, that's why we didn't carry along that portion of the conversion factor. Does that make sense? Okay. So VAB would be 208 positive 30. VL is just representative of the magnitude. So I just want to be clear about that. So the line, yeah, the line voltage VAB would be 208 angle positive 30, which means VBC would be 208 angle negative 90, which means VCA would be 208 positive 150, or whatever 90 minus 120 is, negative 210, I think. Yeah. Okay. All right. Lots of more example problems on Friday, which will hopefully clarify some things and all that jazz. So I'll see you guys then.